Hi, I'm Darshana Sharma, and here's my presentation on Lab 4 bar magnets. The purpose of this lab was to measure the distance dependence of the magnetic field due to a small bar magnet and compare this value to the distance dependence found using the Beer-Savart law in a computational model. We also did this to understand the concept of magnetic fields and magnetic moment. A preview of my results is that I got an experimental magnetic field of 5.538 times 10 to the negative 5 teslas, a computational magnetic field of 3.102 times 10 to the negative 5 teslas, and I found that the net magnitude of the net magnetic field will increase as distance decreases. So as the two objects get closer together, the magnitude will increase. The models and fundamental principles used in this lab were one, Biot-Savart law, which helps me relate the magnetic field to the current in the magnet. Another two important fundamental principles used were magnetic field of a ring and magnetic dipole of a ring to help us understand the magnetic field in relation to the shape. And we also use the distance dependence formula of a bar magnet to help us understand how the magnetic field will change in relation to distance. We also use off-axis magnetic field and on-axis magnetic field to help us understand the magnetic field and how it changes when it's in line with Earth's axis versus when it isn't. And some other concepts used is that the bar magnets act as magnetic dipoles as the field comes out of the north end and goes into the south. This helps us also understand that the current loops are also acting as magnetic dipoles, and the moving point charges create the magnetic field. So my experimental model, first we assume that the bar magnet acts as a dipole and the system is a phone and the magnetometer and the surroundings is everything else, including the bar magnet, the table, and the earth, as these things all impact the magnetic field in some way. So this experimental setup, first we have to calibrate the Tesla meter app by rotating the phone on the table and obtaining an X value close to 0. This aligns my phone with the north and south axis. Then I slide my phone perpendicularly and horizontally to find where the X and Y components are maximum and use tape to mark, and that's where the magnetometer sensor is the strongest. So for my on-axis measurement, data was collected by finding what the on-axis distances were when the x component of the magnetic field was 20, 70, 120, 170, and 220 microteslas. And three trials were collected, and these values were linearized by taking the natural log, then graphed. And this equation for the line is very important later on. For our off-axis measurements, data is collected by finding the on-axis distance where the net magnetic field is 100 microteslas and recording the y component. Then you move your phone perpendicular and record the magnetic field in the x, y, and z directions. And then to get the correct y component, we have to subtract the measured y component by the Earth magnetic field, as we're in here. So for my calculations, I use a distance dependent formula and then I use my log of distance dependence formula, and this was helped me get the slope of my line. And then I rearrange to solve for the magnetic dipole using this formula that's kind of a variation of Biot-Savart law. And I rearrange to solve for mu naught to get k times r to the power of n plus 3 over 4 pi e to the negative 7. So k is just e to the power of the y-intercept, which gave me 3.19 times 10 to the negative 6. N is just my slope of the regression line, which gives me negative 1.6862, and R is just 1. So it's for mu naught, I got 2.5385 newton meters per Tesla. So my observations were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. This helped me understand the magnetic field in relation to the magnetometer a little better. My computational model, first I calculate using my mu naught to get the magnitude of my mu, and then I get my magnet.mu by getting that magnitude and getting mu hat, and I create a function to for the magnetic field using this mu value. And then I create 6 observation locations and I draw 2 arrows to represent the magnetic fields on axis, draw 4 arrows to represent the magnetic field perpendicular to the axis. This helps me understand the direction of the force in relation to my bar magnet. And then I average my distance perpendicular for my experiment, and then I draw an arrow to represent the magnetic field at 45 degrees from the axis. So here's my final result. So as you can see here, I have all arrows and observation locations accounted for in relation to my bar magnet, and here are all my values. And my magnitude of B at 45 degrees at distance D is 3.102 times 10 to the negative 5 Teslas. So potential sources of error were incorrectly calibrated magnetometer and outside magnetic fields affecting the system, as the tables we used have like wires and stuff underneath which may have affected the system. Another thing is imprecise measurements of distance, and some model discrepancies were that although the model was exposed to outside magnetic fields from the table and other groups is bar magnets, our measurements were likely accurate as we treated the bar magnet as a magnetic dipole. So here are my experimental and computational values, and I have a 56.4% difference between them. So if we hadn't oriented my experiment to compensate for magnetic north and instead just laid it out at some random angle, my data would likely be skewed as the x component wouldn't be calibrated to Earth's magnetic field. However, it would be skewed by the same number. This could be remedied by subtracting it from the total magnetic field. And if I were to stick two identical magnets together and run the experiment again, the direction of my measurements would likely be the same, but my magnitudes would differ and would double as the magnetic field experience at a point would double due to the two bar magnets. Thank you.